Welcome back. If you remember last time, we looked at an example problem where it asked us to use variable specific heat, and I said, well, let's not do that yet because we haven't talked about variable specific heat yet. Right? Let's in the last problem we solved that problem using constant specific heat, which requires a guess and check approach because we didn't know both temperatures. However, there is another way to approach that kind of a problem. We could use what we call the variable specific heat approach. So what that means is recall from, I think I mentioned this previously, in ideal gas, in your ideal gas tables, you have these S naught values, which I said those are not S values, those are not entropy values. And also in the 10th edition, they've now added these S plus values, also not S values. Let's talk about what those are. If we are to look at the Gibbs equation, right, if we're to look at the Gibbs equation where S2 minus S1 is equal to this integral from T1 to T2 of C sub P dt over T minus R ln P2 over P1. We could look at any version of the Gibbs equation, for an ideal gas, and they kind of look the same. There's differences, depends on how they're derived, but this is one version of them. And what we normally do is we approximate this kind of like we did in the last problem. We approximate this as, C sub P is constant, pull it out, then it's just integral dt over T. That's natural log T2 over T1, okay? But if I leave it as the integral form, this is what it looks like. Now, notice that the change in entropy is not just a function of temperature. Right? If you look at table A17 here, you see what I mean that, or hopefully this helps, is notice that in this table, I've got temperature and my H and my U values are functions of temperature, but then I've got this S naught or this S degree value, which is only a function of temperature, right? It's only a function of temperature. Now notice from Gibbs' equation here that delta S is a function of temperature and other properties, not just temperature alone. This S naught value does not describe the part that is not temperature-based. It only describes the part that is temperature-based because this is only a function of temperature, right? So what we find, so what these do for us, these S naught values, then allow us to describe, quantify, portion of the entropy change that is a function of temperature. So S2 minus S1 is equal to S naught 2 minus S naught 1, but then minus this R ln P2 over P1. The S naught values can take the place of this integral, T1 to T2, C sub P dt over T. This version still has the minus R ln P2 over P1. Now, in the 10th edition of the text, they have added these S plus values. So S2 minus S1 is also equal to S plus 2 minus S plus 1. This version has the plus R ln V2 over V1. Those are specific volumes. This is the other version of the Gibbs equation, right? This version, because this is equal to where I've got the integral from T1 to T2. This version has C sub V dt over T. And this one has plus the R ln V2 over V1. So variable specific heat basically says instead of assuming the specific heat is constant and pulling it out of the integral, right? If I assume constant specific heat, I'm making an approximation where I say that this is C sub P at the average temperature times the natural log of T2 over T1. And this one has minus R ln P2 over P1. This is what we call constant specific heat. This is constant specific heat. Variable specific heat says S2 minus S1 is equal to S not 2 minus S not 1 minus R ln P2 over P1. This is what we call variable specific heat. Tried to fix it. Variable specific heat. And these are now table properties. These guys here are table properties. So using this approach, we might have to guess and check to get to C sub P average. Using this approach, I might have to interpolate to find properties out of the property table. But either one's correct, either one's just fine. We're solving it the same way. It's just, do you want to use table properties or do you want to use specific heat at the average temperature? And either one is just fine. I'm going to stop on this one here, and then we're going to work an example problem real quick.